Hi friends, here in this video we are going to see a problem on simple stresses and strain. For that, here is a question. It is given two vertical rods, one of steel and other of bronze, suspended at a distance 600 mm apart. So two rods are given, in between their distance is given, and here the diagram is not given into the problem. We have to remember, we have to draw the diagram on our own. So reading the question is quite important here. Each rod is 3 meter long and 12 mm in diameter. That is, both steel and bronze rod are equal in length and diameter. And a horizontal crossbar connects the two rods, and on it a load of 4500 Newton is placed so that the crossbar remains horizontal. Find the position of the load. We have to find the distance at which this load is kept and the stresses in each rod, that is in steel and bronze rod. Young's modulus for both the materials are given. I'll write the data along with the drawing the diagram. So here into the question it is given that two vertical rods, one of steel and other of bronze, suspended at a distance 600 mm apart. I have shown it onto the diagram. Then each rod is 3 meter long. For steel rod the length is 3 meter. It is 3000 mm. Similarly, for bronze rod, the length is same, 12 mm in diameter, so area would also be same. Area would be pi by 4, 12 square. It gives me the value as 113.097 mm square. Same value of area. Next, a horizontal crossbar connects the two rods, and on it a load of 4500 Newton is placed so that the crossbar remains horizontal. So here there is a crossbar over which a load is placed. (4,500 Newton), and it keeps the bar horizontal as given in the problem. We have to find the position of load on the crossbar and stresses in each rod. So to find the position, from left hand side I'll say that the distance is x, which we have to calculate, position of the load, and stress in steel rod and bronze rod denoted by sigma suffix b. Now with the data understood, we can solve the problem. Now how I would be solving this question is, since both the rods are subjected to the same load, this can be treated as a problem of bars in parallel where the strain in both the rods are same because the lengths are same and subjected to same load. So I'll start the solution part. That since for bars in parallel, the strain in both the materials are same, so strain in steel and strain in bronze, they are same. Strain is stress upon Young's modulus for steel and for bronze, that is from Hooke's law. So therefore ES would be shifted onto the other side. The value of Young's modulus given in the problem, it is for steel 1.96 into 10 raised to 5 megapascal. It means 1.96 into 10 raised to 5 Newton per mm square. Similarly for bronze, 0.63 into 10 raised to 5 Newton per mm square. I'll put their values. Sigma S comes out to be 3.11 sigma suffix b. Equation 1, that is the stress in steel is 3.11 times greater than the stress in bronze. Now, I'll also write the relation that stress is load upon area. So, load in steel upon area of steel. Similarly for bronze. Since both the area are same, they can get cancelled out. So load in steel is 3.11 times higher than the load in bronze. So this is the second equation. It means whenever we have stress relation, in a similar manner we can get the load relation as well. And since here the area was same, I cancelled this area. Now I would be drawing the FBD for the rigid bar or the crossbar which is connected over here. Since the load is acting in the downward direction, both the materials would resist the load by offering reactions in the opposite direction. So drawing FBD, that is the free body diagram. For the crossbar, so here we can see that when this load is acting in the downward direction, there are reactions offered by both the material, that is steel and bronze. The reaction offered by steel is P suffix S, similarly for bronze P suffix B. So I'll use the condition of equilibrium. The first condition is summation of all vertical forces, summation of Fy is equal to 0, because here we have only vertical forces. Convention, upward forces are treated positive and downward forces negative. So therefore we have PS plus PB minus W is equal to 0. Therefore PS plus PB minus W, when it goes onto the right side, it becomes plus W. Now, as we can see from equation number 2, PS is 3.11 times of PB. I'll put this value. W is given as 4500 Newton, and here I'll write down that we can refer equation 2. So here the coefficient is 1. 3.11 plus 1, that becomes 4.11. So 4500 divided by 4.11, that gives me the value of P suffix B, that is the reaction offered by the bronze rod or the force acting in the bronze rod. The answer is 1094.89 Newton. This PB value again I'll put in equation 2 to get the answer of PS. it is 3.11 into 1094.89. So therefore P suffix S comes out to be, so when I multiply this, I am getting the answer as 3405.11 Newton. So this much is the load which is acting on, or the reaction offered by the steel rod. Now after getting this, we have to also find the value of x, that is the distance at which this load is kept. Once we know the reactions offered by steel and bronze, I can take the moment. For example, if I am taking the moment at, suppose, point this, I'll just give it the notation that this is point A. So when I'm taking the moment at A, I can easily calculate this distance x. So the second condition of equilibrium would be used. Summation of moment about point A is equal to 0, where the convention is clockwise moments are positive and anti-clockwise moments are negative. So therefore, here we have minus PB, because it is producing an anti-clockwise moment, minus PB into 600 plus this W is acting in the downward direction, so it is producing a clock moment when I take the moment at point A, W into X is equal to 0, and the moment of this P suffix S, load in steel, the moment is 0 because there is no difference between this point and the load, no perpendicular distance, so the value of moment is 0. So here I would be putting the values. Minus PB into 600, it would go on to the other side. W value is 4500 into X. So, and PB value is 1094.89 into 600. So from this, I am getting the answer of X, and it is 145.98 mm. So very close to 146 mm, approximately equal. So the load should be placed at a distance of 146 mm from point A, or from the left hand side. That's the first answer. Now the next part is we have to find the stresses in both the materials. So first I would be calculating the stress in bronze, that is sigma suffix B. The stress in bronze is load in bronze upon the area of bronze. PB is 1094.89, area is 113.097. So from this, the stress in bronze comes out to be 9.68 Newton per mm square. That's the second answer. In a similar manner, we can find the value for steel by using load upon area, or simply we can use equation number 1, where it was the relation of stress. Sigma B is already known. I'll put the value in equation 1. So sigma S is 3.11 into 9.68. So therefore, the stress in steel comes out to be 30.10 Newton per mm square. So that's the third answer. And when we see the data, we have found the distance at which the load should be placed and the stresses in both the materials, and with this the problem gets completed. At the end, if you'll find my videos helpful, you can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.